Applied geometry. So this is a lesson on symmetry. Please make sure that you have in front of you the notes. They're actually the lesson slides so that you can follow along with me. Make sure you write down everything that I write up here in your notes and keep them with you so that you can do the exit slip and the homework at the end of the lesson. Yes, there's homework today. Haha. So here is, oh, hold on, computer is going slow. All right, so we're going to learn about two different kinds of symmetry today. There's line symmetry and there's rotational symmetry. Line symmetry, I'm pretty sure you've already learned about before. It is symmetry with a line of reflection drawn on an object. So this is your traditional symmetry. Okay, so if you think of like the human face, if you draw a line straight down the middle of your face, then it is the same on both sides. So you have a line of reflection down the middle of your face. So it's line symmetry. If you look at a butterfly, if you divide it right down the middle, it's the same on both sides. So that has line symmetry. If you want to think of a square, you can divide that 4 different ways. You can fold it in half 4 different ways and have it be the same on both sides. So that has line symmetry. So this is your traditional symmetry that you would think of whenever you think of symmetry. Okay, so line symmetry, and the key word here is it's associated with reflections. Okay, so looking at this figure here, so butterfly. So where's the line of symmetry at? Feel free to yell it out right now. Go for it. So it goes right down the middle, just like that. Okay. What about this flag right here? Take a couple seconds to look at it. Okay, see if you can figure out where the lines of symmetry are at. There are multiple lines of symmetry. Take a couple seconds, point, yell out. All right. So there's one straight down the middle here. Okay. You probably saw the one that goes down the middle here. Did you catch the one that goes diagonally? The line of symmetry right there, because if you folded it along that line, it would be the exact same on both sides. So there's a line of reflection there, and there's a line of reflection there. Okay. So this has 4 lines of symmetry. What about this one? Take a couple seconds, look at it, see if you can decide how many lines of symmetry it has. Okay. See if you can draw in the lines of symmetry. Okay, this is a little bit more tricky to draw in the lines of symmetry on. Okay, so you probably saw this one right here, right? If I fold it along that line, it has a line, or it's the same on both sides. Okay, do you see the other ones? Very good. All right, so one right there, one right here, one right here, and one right here. So basically one that goes through each point. Okay, so this guy has 5 lines of symmetry. All right, so on your piece of paper, take a couple seconds here. Draw an object that has exactly 2 lines of symmetry. So no more, no less. Exactly 2 lines of symmetry. Go for it. See what you come up with. I'd be interested to see some of the figures you came up with. One that I can think of is an oval. That would have 2 lines of symmetry, one going this way, one going this way. You could have had a rectangle, not a square, but a rectangle. That would have 2 lines of symmetry, one going right here and one going right here. Notice that the diagonal is not a line of symmetry for a rectangle, because if you folded it along that diagonal, this part would come down about right there, and that would come up right here. So they aren't the same on both sides. Okay, very good. Go ahead and try and draw one that has exactly 3 lines of symmetry. Take a couple seconds, see what you come up with. Try it with exactly 3 lines of symmetry. No more, no less. All right, so what did you come up with? I'm thinking probably at least one person has this on their paper. Lateral triangle. It's divisible this way, and this way. So it has exactly 3 lines of symmetry. anything else that you have that has 3 lines of symmetry would count for this. So I'd be interested to see what you have. We're having technical issues here. I'd be interested to see what you have. All right, so what transformations of line symmetry remind you of? Okay, so I'm really trying to get you to see that reflections are associated with line symmetry. So reflections are the name of the game with line symmetry. So this leads us to what do we have when we have other kinds of transformations going on. So this leads us to rotational symmetry. Okay, so rotational symmetry is symmetry in which the object matches itself when it is rotated. This is kind of cool, okay? So if you take a figure and you rotate it around and it matches up on top of itself, okay, that's when you start having rotational symmetry. So I like to think a lot of like snowflakes. So if you take a snowflake, I'm going to try and give my best artistic impression here. One example, okay? So let's say we have a snowflake that looks like this, okay? Assuming that my drawing showed that they were all evenly spaced around, if I took this snowflake and I rotated it, I took it and I spun it around, so I took it, oh, so you see how when I rotate it around, if they're all evenly spaced, I end up on top of myself over and over again with that snowflake. Okay, so this snowflake has rotational symmetry. Okay, there's 2 things that we use to describe rotational symmetry. So you know how with line symmetry we talked about the line of symmetry, the line of reflection that we could draw on the object. When it comes to rotational symmetry, we're going to talk about 2 things. It's angle and it's order. Okay, so the angle of rotation is how far I have to rotate it before it ends up on top of itself again. So please watch carefully to what I'm doing here. Okay, so I have this square here. And I'm assuming I just labeled or made the vertices of it colored just so that I could see whenever I turn it what the different vertices are. But whenever you're rotating it, please do not worry about the colors matching up. Okay. So when I rotate this 90 degrees, so I'm rotating, 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 rotating. Aha. Notice as soon as I rotated 90 degrees, it matched up with itself again. It's in the same position that it was when it started. I can take it and I can rotate it another 90 degrees, and it matches up on top of itself again. Okay, so this is rotational symmetry, and its angle of rotation is 90 degrees. I'm rotating it 90 degrees before it matches up on top of itself again. Okay. Order of rotation is how many times I will rotate it before it comes back to the beginning of it. Okay, so if I take this, I have this square inside of a box so that I can see whenever I rotate it what happens to it. So if I take it and I rotate it once until it comes back to itself. There we go. So I've rotated it once, right? Let's rotate it again. And it matches up again. So now I've rotated it 2 times. Let's rotate it again. All right, now I've rotated it 3 times. I'm going to rotate it one more time because remember I started with the orange square up there. So I'm going to rotate it one more time and aha. Okay, so 4 times it took to rotate it around, to click it around until it came back to where it started at. So its order is 4. Okay, so angle, you give me an angle measure, how many degrees you had to go before you came back to what it looked like again. And then order is how many times you click it around until it comes back on top of itself where it started. Okay, there is a relationship between order and angle. If you think about it, there's 360 degrees in a circle, right? If you go all the way around, it's 360 degrees. Well, if I'm going all the way around with my order, I'm clicking it around that many times. That means if I take 360 degrees and divide it by my order, that should give me my angle. We can test that with the example that we just did. Okay, so we can take 360 degrees, divide by 4, and notice that is 90. So my order of that square was 4, and so my angle is 90 degrees. Okay, so Just so you can think about this, do objects have both line and rotational symmetry, or can they? And I say the answer is definitely yes. Okay. Think back to some of the examples that we did earlier. So, for example, this guy right here. So he has line symmetry, right? Does he also have rotational symmetry? Take a second and look at it. Indeed, he does, because look at him. I can take him and I can rotate him. And looky there. It looks exactly the same as what it started with. I can rotate it again. And looky there, it looks exactly like what it started with. I can keep doing that. Notice how many times I go around before I come back to the way it was oriented at first. How many times did I click it around? Go ahead, yell it out. Yes. So it is 5. So this would be my order. Okay, my order is 5. So now if I want to know my angle, all I have to do is take 360 divided by 5. And you will find that that is, hold on a second, gotta do this in my head. 7, carry 1, 72. So 72 degrees is my angle. So if I rotate this star 72 degrees, that's when I come upon the next point. Okay. What about, hold on, my board's freezing up a little. There we go. What about this guy? So he has line symmetry. Does he also have rotational symmetry? Yeah, definitely. Okay. So if I take him and I rotate him like this, hey, he looks the same again. If I rotate him again, hey, look, he looks the same again. And if I rotate him again, hey, look, he stays the same again. And one more time, and I'm back to the way that he was facing the first time. So how many times was that clicked around? What's my order? Go ahead, yell it out. Nice loud. Yeah. So the order is 4 in this case. So that means my angle is going to be 360 divided by 4, or 90 degrees, which makes sense because it's basically a square with stuff inside of it. So our square that we did before had order of 4, angle of 90 degrees. So does this guy. What about, come on, board, keep going. My board is not responding right now. Okay. What about this one? So this one has line symmetry. Does it have rotational symmetry? Think about that for a second. Does it have rotational symmetry? Yeah. Okay, so if I take it and I rotate it, it doesn't look like what it started with. Still doesn't look like what it started with. That's pretty upside down, but that's not what I started with. So this one I had to go pretty much all the way around before I came back to what I started with. That's not rotational symmetry. So this has line symmetry. It has no rotational symmetry. Okay. All right. Just so you know, so this is just a little teaser for what we're coming up on next. Okay. So regular polygon. A regular polygon is a figure polygon. It's a figure that has all congruent angles and all congruent sides. Congruent means the same. So that means that whenever you look at this figure, it has all same angles, all the same sides. So for example, a square would be considered a regular polygon. It's a 4-sided figure in which all of the sides are the same, all of the angles are the same. You could also, I'll use my drawing tools here. Here's what a regular pentagon would look like. Not like that. So you see all the angles are the same size, all of these sides are the same. Okay, so that's what a regular polygon is. And whenever we get into that, we'll actually figure out with a regular polygon, we'll be able to calculate its angles, and we'll also be able to do something called a template. I just wanted to get that into your notes right now so we can use it later on. Okay, so remember our target today was to be able to identify objects with line and rotational symmetry. Remember, line symmetry is like reflections. You can draw lines of symmetry on things and be able to see that both sides are the same. You can have rotational symmetry, which you describe using an angle and an order. Order is how many times you click it around before you come back to where you started, and then 360 divided by your order gives you your angle.